Hello everyone, I am Pushpita Chandra. I am a PhD student at IIT Delhi under IIT Delhi and University of Queensland enjoying PhD degree. So I am the TA for this course and introduction to laser and laser systems, and this is week 4. So let us start with today's tutor in session. We will first discuss polarization, specifically the cluster angle. Then we will like how this booster angle helps the concept of booster angle and then we'll see how the game is efficient, not efficient. The company is actually is achieved in continuous laser, steam laser, and pump laser, and pulse laser, not pump laser, pulse laser. So, CW laser and pulse laser, and eventually, very efficient for lasers. So, basically, what is the electromagnetic like transfer electromagnetic radiation describe the quality of radiation. Describes the orientation of its oscillation, especially for the electric vector of field. that is polarization. And as primarily, I think you are all aware of basic optics properties, and polarization is being discussed in basic optics classes or courses. The polarization can be a different area. Also know how to like describe them mathematically, and we also know that linear polarization and circular polarization are essentially a special type of elliptical polarization. So we don't need to go there in this course. So we just say what is polarized, like not polarized, like so in a horizontally polarized light, the electric field oscillates in a horizontal plane. Electric field oscillates in horizontal. For is polarized light. The plane of oscillation for electromagnetic wave always contained in the particle plane. So the previous class, put like uh, it's like similar way from the price price that so Now we come to the concept of rooster angling. If the people is like so it's like for it's like so it's like so use like like this will be like yes. So that's the case. So you see this is you like this. So I need reference in terms of so for like if it is for my interface, it's like with for people it's like if it people it's like so if people is like for someone this particular is for the random it will be any reflection for people is like so on the kids and always like so this function of so people will get as you so you will get you know or uh, fiction like you only get as well as because no people right so this is how you get polarized with from an unpolarized with so P is for regional, and so the I is the P show that mathematically when the wave is directed and transmitted and reflected over the transmitted wave. So I the I to be we can see the degrees the this is reflection. R is reflection. R is minus so how this is 90 what is happened and B is basically into we from that in this law says that you know sign B into sign theta T we say So we know that this is we know so that comes from n1 sine theta a from this is equal to n cos theta. From Brewster's relation with this and from here we got this. So from 1 and 2 we got sin theta pi cos theta b. So was sin theta sin cos theta b. So cos theta b can be written as theta b and cos theta b is basically sin 90 degree minus theta b. So theta r 90 degree minus theta. So theta b is equal to just theta I theta b theta b theta b. So it's 90 degree minus theta effective. So theta r plus theta effective. So Brewster angle reflected. And transmitted rays particle. Now we can question how come we find that? That is basically n1 sine theta I is equal to n sine theta r. So n1 sine theta 1 is equal to theta b and n2 sine 90 degree. So that will be n theta b B is and we must end so now is we should regarding the stress angle. So why we say that like uh, is zero equals right so this point of investigation like is is given by that square like this theta so yeah understood what you do I just and 90 days, which may have this week. So, of contribution, depends on the the line. See reflective index duration. Theta B is tan inverse N2 by N. N2 is the refractive index of the second medium and N1 is the refractive index of the first medium. So this basically depends on the refractive index. The answer would be this refractive index. And question number 2, certain medium Brewster's angle is 56 degrees. The refractive index of the medium is A 1.48, B 1.33, C 1.4, D 2. So in this question, it is given in 1 is equal to 1. So in that case, tan theta B is equal to N2 by N1. That is N2 gain. So theta B is basically tan inverse N2. So here we need to calculate N2. So that is basically tan theta B. So tan 56 which is almost equal to 1.4825. So this is the answer basically. So CW laser and the continuous wave laser, that is basically the output power with time is continuous. But for pulsed laser, the output power is basically like this. So for CW laser, we need population inversion continuously. So the pumping should also be done continuously. But for pulse laser, the population inversion should be around this time when the pulse is created. Then you stop, then again population inversion we needed when another pulse is came. So here the pulse repetition rate, like pulse repetition rate is basically per second how many pulses are there. So it can be very high or also very low, that if the pulses are like this and this, that there is very much time gap. So in the CW mode, continuous operation is possible for a 4-level based lasers, and the maximum achievable power is limited. And we need to overcome the operating, this maximum uh, limited uh, maximum achievable power, and also the heat generation during the continuous population inversion and all those in the CW laser. But in the pump laser, basically, we can achieve the higher output power than the CW laser, but it is not continuous, it is in pulse mode. And the peak power pulse in pulse laser can be increasing both the amount of pump energy and the rate at which it is deposited into the media. So if more energy is pumped in a shorter time, population inversion will build up more rapidly, pushing the peak power further up. Scaling up the power of the laser pulse cannot occur indefinitely. There should be a limit. So if the output power get increased, so you will see that the first pulse for any laser, we expect a steady output. But that doesn't happen in the real world. Okay. So when we say steady output, that means this line for CW laser should be the same. There should not be some kink like this and all the things. It should be perfect, parallel, straight line. And for pulse laser, this height of the pulse should be of the same. But if you start increasing the like power, like pumping, um, pump laser power, you are increasing, or anyway you are increasing the pump power. So you will see that if the pulse repetition rate is very high, after some time the pulse height will get decreased. But if your pulse repetition rate is low, you might not see that thing, that the pulse height is being getting reduced at certain up to a point, but it happens like after that. So basically, if your pulse repetition rate or the time between two pulses is large, pulse repetition rate is low, or the time between two pulses is large, you can increase the pump power up to a certain point. But if your time between the two pulses is less, that certain point comes very faster than the other laser. So if you're there are three different kind of pump power. So that is small, different pumping rate: small, moderate, extremely rapid. For this small pumping rate, the pump power is defined by like this. For moderate, it is a bit skewed. For extremely rapid, it is like go up and like this. So for this, population inversion takes some time. Like at this point, population inversion is achieved. So that how it comes. But for this laser, that come at a very faster, basically. So faster than uh, the pump, faster than the laser, which pump power is, and it is extremely faster. This it will get population inversion very fast, very fast. Laser output we get here. So that is the laser output. This laser is a bit higher than this, and that laser output is much more. Peak power is much more. So this is the output, laser output. This is population inversion, and this is pump power. So if you increase the pump power, laser output will be high, but it also depends. Like if your pulse repetition is rate is very low, you can increase the pump power up to a certain point, and if your pulse repetition rate is very high, so that certain point comes very faster. So we already have discussed the various pumping method. Optical. So in optical, there are two methods: conventional light and another is electrical. And in two way you can do the pumping, like side pumping. So in this case, the active medium is here, and the pumping can pump power can interact with active medium naturally. So in this case, current flow transversely, and another method is end pumping. In pumping, the active medium is like this. Draw differently. So the pumping enters at that position. And in this case, the current flows longitudinally. So when conventional light is being used, so there is a for CW laser the pulsed laser comes as conventional pumping linear optical laser pumping. So for CW, this is the method. This is the CW laser. The active medium can be active medium, solid, liquid, gas. For pulse mode also, the active medium can be solid, liquid, gas. For optical laser medium, that is for CW, that is also solid, liquid gas, and also solid liquid gas. So for that, is it stable? So for when you are using conventional optical pumping method for CW laser, when active medium is solid and liquid, uh, the stability of the skin is stable. But for gas, it is not stable. Pulse also, it is stable, but it's not stable here. But for CW laser, where the pumping method is also laser, we can also use gas medium. Remember, when you are using conventional pumping method, you can only use active medium and solid and liquid as active medium. But for CW as well as pulse mode laser, but for when you are using the like laser uh, suitability of the scheme is all for solid, liquid, and gas. But it is more prominent to use in gaseous method. But also the nowadays the laser has been using as a pump uh, procedure for solid state laser also. And there the active medium is not gas. And how it's been given. So generally, end pumping is being given when the laser is being used as a pumping method. But when the basically conventional optical sources have been used, so side pumping is given. For electrical pumping also, only solid and gas medium we can use, and we can use in for electrical pumping. Basically solid and gas medium is being used, and end and side both are like scheme is appropriate. So optical pumping by conventional sources. So in that case, basically arc lamp is being used for CW lasers and slash lamp is used for pulse laser. So that is intuitively that for CW laser we need continuous population inversion. Inversion for flash lamp pulse or pulse laser, we don't need continuous population inversion. Now, basically, for CW laser, the operation of typical arc lamp pump CW laser is basically like this. This is the cavity. And between the cavity, there is active media. And this is a reflector. So here we put the arc discharger here. So there is an anode. This is anode. And this is cathode. Here noble gas is present. And this is quartz tube. So the resistance is added as a parallel. This is power supply. And laser beam is coupled out of inlet direction. That is the case. So the application of appropriate voltage between the two electrodes fixed at the two ends of the quartz tube strike an arc discharge in this noble gas contained in high pressure in the tube. Here is the high pressure tube. Initial boosting of this applied voltage through some electrical manipulation is prerequisite, as discharge impedance at a high gas pressure is too large initially for just the power supply voltage to take over. Because of the non-ohmic nature of the impedance of the gaseous discharge here, the real resistance R is usually connected in series, because the impedance is non-ohmic. So the R is being connected as a series to stabilize the discharge. So the filamentation of the discharge results in gently enhancing the density of the current flowing through it. Thus, in turn, causes the tube to emit light spontaneously all around it and intensely much higher than the possible with the conventional fluorescent light, making the arc lamp suitable for pumping a CW laser. The lamp of nearly the same length as the active medium is obviously placed. The lamp and the medium is of the same length. And they are enclosed in a hollow cylindrical reflective cavity. So the here this is high gas pressure. So because of this thing, the lamp emits light over a wide spectrum of wavelength, of which only a fraction contributes to the pumping of the species from the ground state of the lasing medium. Longer wavelengths detrimentally impacts the operation of the laser by contributing the origin of thermal lensing. In order to enhance the efficiency of pumping and minimize this effect, the inner surface of the infusible is often coated to reflect shorter wavelength and thus absorb or transmit the longer wavelength. So basically, to absorb and transmit the longer wavelength, which causes thermal lensings So what is thermal lensing? Basically, due to this thermal lensing, all the like here in the quartz in the laser, the fraction of the pump energy that sits back in the system is often dissipated heat into the lasing medium. In the case of solid state laser, its active medium is basically laser rod, and in this rod, they are established a variant refractive index gradient. So that hampers the performance of the laser greatly. So the active medium is not that does not act as a homogeneous medium. It acts as a layer of different medium with different refractive index. So that causes the degradation of the lasing effect. This is for optical pumping with RPM for CW lasers. Now optical pumping by slash lamp for pulse laser. So here basically what happens, this is here it is the active medium. Then the quartz tube is here a bit wide. Noble gas is also there. This, this is anode. This is cathode. And this part is inside a reflector. Okay. So the anode here is the switch. Here capacitor is in parallel. And suppose there is a resistance and power supply. Okay, so here what happened in the conventional operation, a high voltage power supply first charges up a condenser C through a charging resistance R. Once the condenser has been charged to an appropriate voltage, a high voltage, high current switch placed in the discharge loop. This is the discharge loop containing the capacitor and the flash lamp is made to close, and this switch has been closed. The closure of the switch in turn allows the capacitor to discharge its stored energy quickly into the flash lamp. So the stored energy goes to flash lamp quickly, and like we will get a flash from the lamp, and that is the pump power for population inversion, and the like basically the laser start emitting the lasing action. That is the lasing action. Now, after the things that then again the C gets charged and discharged. So every time C gets charged, there is no flush. But when it gets discharged, we will get a flush, and when we get a flush, after that we will get a lasing option. So typical UV laser, which is the first laser, used a helical flash lamp as its pump. So here you can see that on the conventional optical method, the pumping method is sidewise, not endwise. That of conventional, like here it is a conventional light. This is active medium. So conventional light discharges in every direction. So it is not that powerful. If the active medium has solid and liquid, then only conventional light source, if it acts as the pump in the side configuration, it will work. But same thing will not work. The active medium has gaseous molecule. It emits light in every direction. So that will not work. So basically pumping action is the photons get absorbed by the species atoms or molecules of that active media. So here only, so it can passes without being absorbed in the gaseous medium. And this is the sideways scheme. But if you place that in an end pumping scheme here, then only a few can interact, even for solid and liquid, let alone gas. So you cannot functional light source as a pump in end pumping scheme. Now optical pumping by laser. So basically we will use the laser where if like the laser bandwidth and the pump laser bandwidth and the laser we are using, the bandwidth will match. The spectral bandwidth will match. But for conventional light, what is going to happen? That is the bandwidth for conventional light, and the laser is working in this bandwidth. So this portion, this spectrum portion is being wasted basically. So that is why we can use the optical pumping by laser, and their active medium can be a gas. So here basically what happened there is the schematic is here M1, the active media is there. Here in scheme in comping is being used. Sorry for the technical problem. method that if we use a dielectric transmit the amplified spontaneous light and wavelength, and there's spontaneous light or wavelength lambda 2 that also got reflected back to the conclave. So it is not selective. So the lasing action is not happening. It is not reaching M1. To solve that, we replace the dielectric mirror with dichoric mirror. So what happened that ordinarily dielectric mirror M3 reflects the light at the light lambda 2, which is the spontaneous light. Mm. So I've now been doing that is dichoric mirror now. Well, previously what was happening that lambda ordinary dielectric mirror M3 reflects light at the pump wavelength lambda 2 will also is being significantly reflecting the light originating from the spontaneous emission at a wavelength lambda 2. Then that will cause we are not using the cavity formation using, and it is not reaching active medium, like it's not reaching the this mirror M1 for the like transmit out of the laser cavity. So we are not getting any output. But in that case, what happened now lambda 2 will not go there. Lambda 2 will go there. Dichoric mirror only reflect lambda 1 and transmit lambda 2. Lambda 1 greater than lambda 2 reflects, and we will get an output. Now, if we want a polarized light from a laser, what will we do? That this is a mirror, this is active medium, and this is mirror 2 in 2. We'll place M3 at Brewster angle. This has to be Brewster angle. So what happened that we'll get here the spontaneous photons emitted by the medium immediately following its pumping act as the seed of the simulated emission to set it. Spontaneous light is essentially randomly polarized, so would also be the light emitted through the simulated emission in the beginning. The random polarization here we can see that at the Brewster angle, P polarization exhibits the transmission, while S components will get reflected. So after a certain time, only P polarization will be there. Get P polarized right out as output. Here the spontaneous another scheme is basically what can you do that M1 here. There is the active medium. This is M2. So what happened? That you can set the pump laser at booster angle. This is theta B. So only parallelly polarized light goes into the active medium and we'll get parallel polarized light as output. So for electrical pumping also, same as CW laser. But here we don't need this novel gas, quartz and all those things. So basically it acts as an anode and that acts as a cathode. Yeah. So this is the electrical pumping for CW mode. And we don't need a reflector also. The same mechanism we follow here and for but instead of like having a quartz out discharge and all those things, directly the electrical plug we draw electric like in optical pumping the electrical energy converted into optical energy and that is using optical pumping. Here directly the electrical energy has been using as a pumping method So in elastic there is for with the electrons there is elastic collision with the species of the active media and transfer their kinetic energy. And transfer kinetic energy. Here what happened? Here also in the pulse length module, it is bit different. So here anode and cathode are not being used at the end of the gas medium and the end of the active medium. Here what happened? That electrodes are placed as like this. This is output mirror here. This is output. This is fully reflective mirror. And there is a switch S, the power supply, the capacitor, fully is for CW laser, and this is electrical pumping for pulse laser. So they are uniform electrode. So it's as the same mechanism of the conventional optical pumping for pulse laser. Here the capacitor got charged, then when it got discharged, here the electrode goes power and they discharge the electrons, and those electrons collide elastically with the active medium species and give them the pumping power. So there another thing we need to discuss, that is efficiency. So if E in is the electrical input, say the pump, due to the pump, we will get, after electrical pumping, we will get EP, that is E in into P by 100. In percent of E in produce photon. Then of this EP, EX percent cause excitation. Then EX would be EP into EX by 100. Of this, T% got T% of the excitation energy is lost. So for the lasing action, we have EX into 1 minus d by 100. So basically EL is E in into E x into P by 100 into 100 into 1 minus d by 100. This is the efficiency of the laser. So efficiency is basically EL by E in, which is EX into P by 100, 100, 1 minus D100. Another term is called quantum efficiency. So quantum efficiency is basically when of all of the pump energy we are giving as an input, that all of the electrical energy we are giving as an input has converted into pump, and there is no loss in the excitation. So basically that is 1 minus d by 100. That is not at all achievable. And there is also pumping efficiency, that is basically Ex by 100. That electro-optic efficiency. The electro-optic efficiency is efficiency. Electro-optic efficiency is defined as the efficiency of the conversion of pump energy, which is essentially electrical in origin. So that is EOE is basically Ex by 100 into 1 minus D by 100. So now we can discuss some questions. The first question is polarization of wave is possible if it is a, a transverse wave, B a longitudinal wave, C both transverse and longitudinal waves, D isotropic wave. So the transverse wave can be polarized because their oscillation is perpendicular to the direction of propagation. So here they are restricting to a single plane. And the longitudinal wave cannot do that. So the answer is transverse wave. Question 4. Correct expression of reduced angle theta as a function of refractive index of the material when surrounding medium is air. We all know tan theta is mu here, mu by 1. So that would be theta is equal to tan inverse mu. Of the different options, theta is equal to tan mu, theta is equal to sin mu, theta is equal to tan inverse mu, theta is equal to cot mu. Only this one is correct. That was this option C. Question number 5. At the Brewster's angle, incident and reflected rays make an angle of 90 degree. B incident and transmitted rays make an angle of 90 degree. C angle of incidence is 90 degree. D reflected and transmitted rays make an angle 90 degree. So we know this is the correct answer. I have already derived it mathematically. Question number 6. If I is the intensity of randomly polarized incident light falling on crystal plate. Basically, the plate is at crystal angle. What will be the intensity and nature of a part of the transmitted light? A I by 2 and S polarized. B I by 2 and P polarized. C I and S polarized. I and P polarized. So we know that only P polarized light will be transmitted. So P polarized light will be P polarized and S polarized light will not be, or some of the S polarized lights will be reflected also. So the portion of the S polarized light will get reflected. So again and again. So the intensity will get halfway. So that's the reason. Question number 7. Emission from a laser is in general a randomly polarized, B is polarized, C p polarized, D circularly polarized. So the emission from a laser is basically randomly polarized. It doesn't have any polarization. But if you put a mirror in the booster angle and all, then you will get p-polarized light. But if you put a booster angle in different angle, booster plate at a different angle, you can get less polarized also. But generally, the if you do nothing, you will get randomly polarized. Question number 8. The peaked the peak power obtainable from pulsed and CW lasers. A is comparable. B is significantly less for pulsed laser. C can't be compared. D is significantly higher for pulse laser. As I have discussed earlier, that you know that pulse laser peaks are very high than CW laser. So basically, this is the answer. Question number 9. Continuous operation of a CW laser is possible only if a upper laser level lifetime is shorter compared to lower laser level. That will not sustain the population inversion, so that is not the truth. Upper laser level lifetime is longer compared to lower laser level. You know that is one of the answer, but let's go to the third and fourth option. So C is both lifetimes are comparable. That will also not possible. D is independent of level lifetimes. That is also not true. Question number 10. The output power of CW laser can not be increased indefinitely by raising the power of pumping because a CW power can be increased without any problem. That is not true. That is not a reason at all. First, that is the statement of the questionnaire. The thermal population of lower energy level increases. That's the one of the region, and that will cause a thermal lensing. So that is the reason. C is it is difficult to remove heat from the glazing material. Also, that is also the reason that the thermal population is causing the thermal lensing effect. It is also the reason. D is upper level lifetime increases. That's not the problem. Upper level lifetime, if it increases, that's a pro for us. Like that's a positive thing, but that's not the case here. So this is for today. More I'll discuss in the next class. Thank you.